Welcome to this coding walkthrough. Today, we'll be tackling the problem +1 from LeetCode. This is a classic array manipulation problem that challenges us to increment a large number represented as an array of its digits. Let's explore the problem, step by step, and discuss various approaches to solve it effectively. Let's dive in. The problem is called +1. Here, you are given a large integer represented as an array of digits, where each digit occupies a single index in the array. The most significant digit, which is the leftmost one, appears at the beginning of the array. Each digit in the array is a number between 0 and 9. The task is to add 1 to this integer and return the result as an array of digits. Additionally, the input is guaranteed to have no leading zeros unless the number itself is 0. Your solution should modify the array to reflect the updated number after adding 1. For the input format, the function receives an integer array called digits, which represents a non-negative integer, and it outputs an integer array that shows the result of performing the addition. Consider the first example. The input is the array 1, 2, 3. This array represents the number 123, where each digit corresponds to a place value in the number. When we add 1, the number becomes 124. Since the output must also be in the form of an array of digits, the result is returned as 1, 2, 4. In another example, the input is 4, 3, 2, 1, which represents the number 4321. Adding 1 to this number gives 4322, so the output is 4, 3, 2, 2. Notice that the array structure remains consistent, with each digit occupying its own position. Now, let's look at another example. The input is 999, which represents the number 999. When we add 1 to 999, the result is 1000. However, since we must return the result as an array of digits, the output becomes 1000. This example highlights how the addition process can lead to a carryover, where digits roll over to the next higher place value. The constraints of the problem are also worth noting. The length of the input array will always be between 1 and 100, and each digit will always be between 0 and 9. Importantly, the input array will not have leading zeros unless it represents the number 0. There are a few edge cases to keep in mind. For single-digit inputs, such as 0, the output should be 1, and 4, 9, the output should be 1, 0, because of the carry. Carry propagation is another important consideration, as seen in the example 999, where the output becomes 1000. Additionally, the implementation should handle large input sizes efficiently, given that the array can have up to 100 digits. Lastly, remember that the input will never have leading zeros except for the special case of the number 0, so an input like 0, 1 would not be valid. These considerations ensure the solution is robust and handles all edge cases correctly. The brute force approach to solving this problem is straightforward and builds on basic intuition. It involves treating the array of digits as a whole number. First, we join the digits together to form an integer representation of the number. Then, we add 1 to this integer. Finally, we split the resulting number back into an array of its individual digits. For instance, if the input is 1, 2, 3, we combine the digits to form 123, add 1 to obtain 124, and then convert it back into 1, 2, 4. While this approach is simple to understand and implement, it has significant trade-offs. The time complexity is linear, O(n), due to the operations of combining, adding, and splitting. However, for very large numbers, we may face issues with computational efficiency since handling such numbers requires arbitrary precision arithmetic, which can be costly. Additionally, the space complexity is O(n) for storing the result. While intuitive, this method can be inefficient for large inputs due to these conversion-related overheads. A more efficient way to solve this problem is to work directly with the array of digits without converting it to an integer. The optimized approach leverages the fact that adding 1 to a number affects only the rightmost digits, with a carry propagating to the left if necessary. Here's how it works: starting from the last digit, we add 1 to it. If this sum is less than 10, we simply update the digit and stop. However, if the sum equals 10, we set that digit to 0 and carry over the 1 to the next digit. This process continues until the carry is resolved or all digits are processed. In cases where the carry propagates past the first digit, such as 999, we prep and a1 to the array to represent the new number. For example, with input 1, 2, 9, we add 1 to the last digit, resulting in 10. We set the last digit to 0 and carry over the 1. Moving to the next digit, we add the carry to 2, making it 3, and stop since no further carry is needed. The result is 1, 3, 0. This method is both time and space efficient, with a time complexity of O(n), since we process each digit once, and a space complexity of O(1), as the array is modified in place. The optimized approach was chosen because it is both efficient and elegant. By addressing the addition directly within the array, we avoid the computational overhead associated with converting the digits to and from an integer. This makes the solution scalable and well-suited for handling large inputs. The key insight lies in propagating the carry as needed, which ensures the operation completes in linear time, O(n). Furthermore, modifying the array in place minimizes space usage, achieving O(1) space complexity aside from the output. In contrast, the brute force approach, while conceptually simpler, introduces unnecessary complexity and inefficiency due to the integer conversion step. By focusing on this optimized method, we ensure a solution that is clean, fast, and capable of handling even the largest numbers efficiently. To start solving the +1 problem, we need to understand the input and the goal. The input is an array of digits, where each digit represents a single position in a non-negative integer. Our task is to add 1 to this number and return the result as a new array of digits. The first step in the algorithm involves converting the array of digits into an integer. Imagine the input array is 1, 2, 3. This represents the number 123. To achieve this conversion, we initialize a variable, say number, to 0. Then, for each digit in the array, we multiply number by 10 to shift the digits left, and add the current digit. This process ensures that the digits are combined correctly. For instance, starting with number equals 0, the first digit 1 gives us number equals 0 * 10 plus 1 equals 1. The next digit, 2, updates it to number is equal to 1 times 10 plus 2 equals 12. Finally, the digit 3 results in number is equal to 12 times 10 plus 3 equals 123. This step lays the groundwork for the next operations by converting the array into a manipulatable integer value. Once we have the integer representation, the next step is to increment the number by 1. This is straightforward, simply add 1 to the value obtained in the previous step. For example, if the integer is 123, adding 1 results in 124. The key insight here is that this simple addition may produce a carry, especially in cases like going from 999 to 1000. After incrementing, the third step is to convert the resulting integer back into an array of digits. To do this, we repeatedly extract the last digit of the number using the modulo operator, number %10, and append it to a list. For instance, with 124, the last digit is 4, so we append 4. Then, we remove this digit by performing integer division by 10, resulting in 12. Repeating this process gives us 2 and then 1. The digits are extracted in reverse order, so the final step is to reverse the list to restore the original sequence. This gives 1, 2, 4 as the final array representation. When working through this algorithm, there are some key insights to consider. First, the approach naturally handles carries. For instance, if the input is 999, the addition propagates the carry through all digits, resulting in 1, 0, 0, 0. Second, edge cases are important to understand. For a single-digit input like 9, the output becomes 1, 0 due to the carry. For an array where all digits are 9, such as 999, the result is 1, 0, 0, 0. However, an empty array is considered invalid input because it cannot represent a number. From a data structure perspective, our input is an array of digits, and the output is also an array of digits. The intermediate integer, number, is used as temporary storage during the conversion process, allowing us to work efficiently with the number before returning the result. Now, let's analyze the complexity of this approach. The time complexity for converting the array to an integer is O(n), where n is the size of the input array. The increment operation is O1, as it's a single addition. Converting the integer back to an array takes time proportional to the number of digits in the result, which is at most n plus 1, so this step is O(m), where m is the size of the output. Overall, the time complexity is O(n). For space complexity, the input and output arrays require O(n) space, while the intermediate storage for the integer number is O(1). Thus, the overall space complexity is O(n). This algorithm is already efficient for small to moderately sized arrays. However, for very large arrays, we could optimize further by directly handling the carry in place without converting between arrays and integers. While this would reduce the overhead of conversions, it would make the implementation more complex. For most use cases, the current approach strikes a good balance between simplicity and efficiency. The problem involves incrementing a number represented as an array of digits by 1. This solution is implemented in the solution class, with the +1 method. Here's a detailed explanation of the code. 1. The input digits is a list where each element represents a single digit of the number, arranged in order. For example, 1, 2, 3 represents the number 123. 2. We start by determining the length of the input array digits and storing it in n. 3. The algorithm processes the array from right to left, starting from the least significant digit. This is achieved using a reverse for loop, for I in range n1, -1, -1. Here, I represents the index of the current digit being processed. For inside the loop, the algorithm checks if the current digit is less than 9. If so, it means that the digit can be incremented without causing a carry. The current digit is incremented by 1, and the updated digits array is returned immediately. 5. If the current digit equals 9, it cannot simply be incremented. Instead, it is set to 0, indicating a carry to the next more significant digit. 6. If the loop completes without returning, i.e., all digits were 9, we need to handle the special case where the number was a series of 9s, e.g., 999. In such cases, the result is a new array with a leading 1 followed by all zeros, e.g., 1, 0, 0, 0. This is achieved by returning 1 plus digits. The algorithm runs in O(n) time, where n is the length of the input array, since we traverse the entire list at most once. It uses O(1) additional space, as the operations are performed in place on the input list. This makes the solution highly efficient for the problem. This is the Java implementation for LeetCode problem number 66, +1. The logic mirrors the Python implementation, traversing the array from the end and incrementing the first non-9 digit. If all digits are 9, a new array is created with a leading 1. Key differences include using Java's int for arrays and explicit array creation for results. For this first example, the input array is digits equals 1, 2, 3. The goal is to add 1 to the number represented by this array. We start by determining the length of the array, which is n equals 3. This tells us there are 3 digits to process. The loop begins with the last digit, at index 2, which is 3. Since 3 is less than 9, we can increment it directly. So, we add 1 to this digit, resulting in digits 2 equals 4. The updated array is now 1, 2, 4. Since there's no carryover, we don't need to process further digits, and the result, 1, 2, 4, is returned immediately. This is the final output for this example. Now, let's take a look at the second example where the input array is digits equals 4, 3, 9. Again, we start by calculating the length of the array, which is n equals 3. The loop begins with the last digit, at index 2, which is 9. Since 9 is equal to 9, adding 1 would cause a carryover. To handle this, we set the digit at index 2 to 0, resulting in an updated array of 4, 3, 0. Next, we move to the digit at index 1, which is 3. Since 3 is less than 9, we can simply increment it by 1, making digits 1 equals 4. The array is now 4, 4, 0. Since no further carryover is required, the result, 4, 4, 0, is returned immediately. This is the final output for this example. In this final example, the input array is digits equals 9, 9, 9. The array length is calculated as n equals 3, and we begin processing from the last digit at index 2, which is 9. Since 9 is equal to 9, we set this digit to 0, resulting in 990. The loop then moves to the digit at index 1, which is also 9. Again, we set it to 0, updating the array to 900. Finally, we process the digit at index 0, which is another 9. This is set to 0, resulting in 000. At this point, all digits have been processed, and since they were all 9, a carryover remains. To handle this, we prepend a1 to the array, giving us the final result, 1000. This updated array is returned as the output. The time complexity of this solution is O(n), where n represents the length of the input array digits. This is because the algorithm processes the array in reverse order, starting from the last digit and working its way to the first. In the worst-case scenario, if every digit in the array is a 9, the loop will execute once for each digit. This is necessary because all 9s need to be set to 0, and a new leading one must be added to the result. Each iteration of the loop involves constant time operations, such as comparing the current digit to 9, incrementing it if it's less than 9, or resetting it to 0 otherwise. These operations do not depend on the size of the digits but solely on the number of elements in the array. Thus, as the number of digits increases, the time taken grows linearly, making the overall time complexity O(n). The space complexity of this solution varies based on the specific case but is O(n) in the worst case and O(1) in the best and average cases. This is because the algorithm modifies the input array in place, meaning it doesn't allocate extra memory for intermediate data structures. However, in a worst-case scenario, where all digits in the array are 9, a new array must be created to accommodate the additional leading one, resulting in a space usage of n+1. For example, for an input like 999, the output would be 1000, which requires additional memory. On the other hand, in the best and average cases, where the array can be modified directly without creating a new one, such as when the last digit is not 9, the algorithm achieves O(1) space complexity because no extra memory is allocated. To better understand this, let's analyze the best, average, and worst cases. In the best case, the last digit is less than 9, such as 1, 2, 3. Here, the loop runs only once, modifies the array in place, and exits. Both time and space complexities are O(1). In the average case, the array contains a mix of digits with some trailing 9s, like 1, 2, 9. The loop processes only the trailing 9s and updates the array in place. Time complexity in this case is O(k), where k is the number of trailing 9s, and space complexity remains O(1). In the worst case, where all digits are 9, such as 999, the loop iterates through all n elements, setting them to 0, and creates a new array of size n+1 to prepend the leading one. This results in a time complexity of O(n) and a space complexity of O(n). By comparison, a naive approach that converts the array to an integer, increments it, and then converts it back to an array also has O(n) time complexity but consistently requires O(n) space for intermediate conversions, which is less efficient in terms of memory. The provided solution improves upon the naive approach by avoiding costly conversions and working directly with the input array. This allows it to achieve O(1) space complexity in the best and average cases. To formally understand why the time complexity is O(n), consider that each iteration of the loop involves constant time operations like comparison, addition, and assignment. In the worst case, when all digits are processed, the loop runs n times, making the time complexity proportional to the size of the input array, or O(n). Space complexity, on the other hand, depends on whether a new array is created. If one is needed, as in the worst case, space usage becomes O(n). Otherwise, the input array is modified in place, leading to O(1) space complexity. Overall, this solution is optimal in both time and space efficiency for solving the +1 problem. In this section, we'll address some common mistakes to look out for when solving the +1 problem. First, let's talk about overflows with large numbers. A common mistake here is directly converting the array of digits into an integer, especially in languages with fixed integer sizes like C++. This can cause overflow if the number exceeds the maximum value supported by the data type, leading to undefined behavior or incorrect results. To avoid this, it's better to handle the digits as an array throughout the computation and skip unnecessary conversions. Another frequent issue is ignoring edge cases. For example, if the input is all nines, like 999, the carry propagates through every digit, resulting in an extra digit at the start, such as 1000. Missing these cases can lead to incorrect outputs, especially as input size grows. The solution here is to always test edge cases systematically, including all nines, empty arrays, and single-digit arrays, to ensure your implementation is robust. Now, let's look at a few more common pitfalls. Mutating the input array is one such mistake. If you modify the array in place without clarifying whether that's allowed, you might violate the problem's constraints or lose points during an interview. To avoid this, make sure to clarify the constraints up front and, if needed, use a separate result array to preserve immutability. Another frequent issue is inefficient carry handling. Some solutions recompute the carry for every digit, which not only increases time complexity but also creates opportunities for bugs, particularly with larger inputs. Instead, handle the carry systematically by iterating from the least significant digit to the most significant, updating the carry as you go. Lastly, assuming all inputs are valid can lead to problems. Inputs with invalid values, like -1, 5, or 12, 3, can break your algorithm. Always validate the input beforehand and confirm constraints during interviews to avoid these issues. When it comes to interviews, there are several insights that can help you succeed. Recognizing patterns is a key skill here. The +1 problem is often a simpler variation of questions involving arithmetic operations on arrays. Once you understand the carry propagation pattern, you'll find it easier to tackle more complex problems, like adding numbers represented as linked lists. Always be aware of edge cases and ask clarifying questions about constraints. For example, inquire about the size of the array, whether leading zeros are possible, and what digit values are allowed. Interviewers also expect an efficient solution, typically with O(n) time complexity. Avoid brute force approaches that rely on string conversions as they may not meet these expectations. Additionally, clarify input constraints early on, such as whether the array can be empty or contain invalid digits. Finally, be prepared to adjust your solution for variations, like subtracting 1, handling multiple operations, or working with different numerical bases. The +1 problem also has close connections to several related problems, which are worth exploring to deepen your understanding. For example, LeetCode 2, add two numbers, involves adding two numbers represented as linked lists. This problem focuses on a similar carry propagation process but works with a different data structure. You're already familiar with LeetCode 66, +1, the problem we're discussing here. Another related challenge is LeetCode 989, add to array form of integer, where the task involves adding a number to an array represented integer. Lastly, there's LeetCode 445, add two numbers to, which requires adding numbers represented as linked lists, but in reverse order. Studying these problems will help you recognize shared patterns and prepare for variations in future interviews. There are several alternative approaches to solving the +1 problem, each with its own advantages and drawbacks. One straightforward method is brute force using string conversion. Here, you convert the array to a string, transform that into an integer, add 1, and then convert it back to an array. While this approach is simple and quick to implement, it's inefficient for very large arrays and can lead to overflow issues in languages with fixed-size integers. A more efficient method is iterative carry propagation. In this approach, you start from the least significant digit, add 1, and propagate the carry as needed. This method operates in O(n) time with O(1) space, making it both efficient and practical for all valid inputs. Finally, there's the recursive approach, which uses recursion to handle carry propagation. While it can be elegant and concise for some scenarios, it may cause stack overflow when dealing with extremely large inputs, so it's less reliable in such cases. Another technique worth considering uses deques for added flexibility. A deque, or double-ended queue, allows efficient insertions and deletions at both ends. This can be particularly useful for variations of the +1 problem that require prepending or appending elements, such as when working with numbers in reversed order. However, while deques offer flexibility, they also increase space complexity, which is unnecessary for the specific requirements of the original +1 problem. Therefore, while it's good to be familiar with this approach, it's better suited for more complex variations or when the problem explicitly calls for such operations. Great job! To summarize, we explored how to increment a large number represented as an array of digits and discussed an optimal approach with O(n) time complexity. Key takeaways include understanding carry propagation and working with arrays for numerical operations. Thanks for joining this session, and don't forget to like and subscribe for more coding tutorials. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!